Malaysian 370, contact Ho Chi Minh 120.9. Good night.
Good night, Malaysian 370.
Breaking news tonight, a Malaysia Airlines flight with 239 people on board, including 4 Americans, has gone missing.
Scripture, the Bhagavad Gita, Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds."
Yo, 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 welcome to the live stream, everybody. Hello to all my 4 Orbsies, everybody. I am Ashton Forbes. Yes, it just happened to be coincidental that my last name is Forbes. No, it's not a massive conspiracy for the people who are wondering. Tonight, guys, on the stream, we're going to be talking about science. We're going to be discussing Attosecond lasers. I want to thank all of you for being here. Please hit the like and subscribe if you are enjoying the content. We just need more science-based content that's out there. And you know what? We do sprinkle a little bit of mystery and conspiracy in. Just the way of the world. Okay. First thing I want to do, guys, is there's a pretty compelling clip, an insightful clip that I want to react to. And then we're going to jump into the science. After that, that'll be the stream tonight. So right off the bat, I saw this about an hour or 2 ago, and it's an interview that Chris Como and Tucker Carlson did. And they're talking about UFO stuff. So I want to react to this real quick because I think it's important.
We just had an election where he was hammering on these things. And even with UAPs or UFOs, whatever terminology you want, we couldn't get more information. These things are all over the place. Sure, some are helicopters, some are fixed wing. Okay, not all of them. And they don't know? Of course they know. They spend hundreds of millions of dollars on the programs. And then we get all our hopes up, right? The media loves mocking News Nation about this because they think that, oh, Cuomo thinks they're little green men in the basement of some building. No, I don't. It's about knowing that we spend hundreds of millions of dollars and use special operators to do things that you won't tell us about. And at a minimum, you should say, well, here's why we won't tell you.
So what are they?
That's exactly right.
Well, but what are they, do you think?
I don't know what the fuck they are. The point is that they know and they won't tell us things. Well, I think it is anathema to democracy.
Can I, of course, I agree with everything you're saying, except one specific point, which is I'm not sure they know.
They have programmed. They certainly know more than we do. Put it that way.
They do. They may know that they don't really know, which is the scariest thing of all. And I've certainly called a lot on this topic. I've stopped talking about it in public. I've tried to stop thinking about it because it's just one of those things that drive you crazy. But my strong impression is that they don't really know, that there isn't a consensus on this, and that they're not, from Russia or China.
He campaigned on it. It was supposed to be a no-brainer, and then they put out exactly what the Biden organization.
No, I'm aware of that.
Administration.
I'm aware of that, and I'm aware of that. That's just my view. I could be completely wrong, but I don't think it's as simple as they know exactly what's going on and they're hiding it.
Well, again, these are your people. Why don't you talk to them? They love you.
Oh my gosh, I have. And
so what do you got for
me?
I
think
come all the way down here.
We don't
cross
know.
all these bridges.
We don't know. And I think that's kind of the scarier answer is
flying over military bases,
shutting them down,
and you
shutting down military.
Yeah, and you don't shoot them down, and then figure out what it was.
Well, maybe you can't. So that's. So look, I think we're getting to the same answer.
No.
If there is a very obvious mystery that's publicly known, there's public pressure to solve the mystery, to divulge what you know, and you don't.
Yes.
Then there's a real reason behind it. It's not just ass covering.
Or do you have the arrogance to believe that you don't have to tell me?
No, not anymore. Not anymore. Because now that, especially in this administration that was elected on the promise of transparency, there's a real reason. Because there's tons of counter pressure. People are aware, like, where the hell are my Kennedy files? What's going on with these things over New Jersey? You said they were over your house in Bedminster. What is it?
Yeah, okay. So let's get into this. I can't believe I'm saying this, but Chris Como is right. Tucker Carlson is laughably wrong. I like Tucker Carlson in almost every situation. I don't know what it is about the UFO topic that makes Tucker Carlson and Joe Rogan. Actually, you know what? I do know what it is that's turning them into idiots on the UFO topic. They're hanging out with the woke disclosure people that are feeding them bullshit. The Gary Nolans, the Lou Elizondo, that whole crew is feeding these guys bullshit. Feeding Joe Rogan bullshit, feeding Tucker Carlson bullshit because they think, oh, well, they're my buddies, so I'll believe what they say about the UFO stuff. And these guys are going, it's like interdimensional. It's like you got to have dimensions. Fucking stupidest shit ever. And they're also saying, oh, we don't know what it is. We just like can't know. Honestly, this is the dumbest argument ever. And I see both sides doing it. The UFO skeptics being like, we just can't know what other physics would be out there. We couldn't understand alien physics. And the believers as well also saying it. We just can't know. We can't understand it. Sorry, it's just beyond understand. It's like, this is the dumbest argument ever. Of course we can. We can at least rule possibilities out. If it's so advanced that we can't, like, get any sensor data on it or figure it out, then we're probably in a weird screwed situation. If there's no biological beings, then it's probably AI based. We can definitely infer some pretty solid. We can rule out some things. Like there's the big board of aliens and what the options are. It's like 40 options. With the government sensor capabilities and what have you, we can definitely rule out the majority of those. So when they're saying we just can't know, that's the biggest line of bullshit ever. Of course the government knows. Some of it's the government. And just like Chris Como said, great points by him. I can't believe I'm saying that again. Great points. He says, well, what if they just can't say it for whatever reason? They don't want to say it. They're embarrassed by it, but they've been doing stuff that they can't admit to. Yes. That's why. We know that's why, because we're seeing them zap MH370. So we know they're doing sketchy ass shit with this technology that they can't admit to. It's darker than just the technology now. It's like, what have we been doing to maintain the supremacy of that technology for national security, right? And of course, if it was some adversary or unknown thing, we would be shooting it out of the sky. Oh, we can't. Oh, okay, we can't. Let's just do normally, right? When we can't figure something out, we just give up. That's how I was taught. Oh, well, look at that. We can't understand that. Let's just give up. It's just the worst lie ever. And it goes with some of what Tucker Carlson said before, where he said he's asked these people about it. He's asked presidents, and they won't say. Well, what does that tell you, Tucker Carlson? What does it tell you that you're asking presidents that trust you, that they will bring you to their house and talk to you, and they won't talk to you about this topic? Yes, it is something dark. It's something big. Are aliens even in the stratosphere of something that would be that big? No, if it was aliens, they would just tell you over dinner. They'd be like, hey, Tucker, turns out it was reptilians all along. Turns out there really is reptilians. They would just say that. What's the national security implication? They might need to tell someone like Tucker Carlson so other people know if that was the situation. It's not about aliens at all. It probably was never about aliens. Even if it came from aliens, it doesn't matter. Think about it. It doesn't matter if it came from aliens. It doesn't matter if it came from Atlanteans. It doesn't matter where it came from. The implication isn't the aliens on our society that they're afraid of for national security. They're afraid of the technology. Okay, so what is this technology that we would be so afraid of? It was about almost a year ago when it dawned upon me. Free energy. The implications of the physics being real are free energy. You just think about that for a minute and you go, oh, wow. Free energy is huge. Free energy does explain why they've been hiding this information, why they've been hiding this UFO stuff. It's not because of the aliens. It's because of how huge a jump the technology is from where we're at right now. And it's not because we couldn't figure it out. It's because we can figure it out, because we did figure it out. It's because we realized right away, oh, here's this whole branch of physics that's been kind of ignored that perfectly aligns with how these aliens are flying around in their ships. For the record, I love aliens, chat. Anyone who says otherwise is a damn and dirty liar. I promised multiple occasions that we would have all the aliens under President Trump. And I tend to deliver on that promise, unlike all the other politicians that are out there. So when the aliens dropped off their free energy technology, thank you very much, we'll take it. Who cares about the rest? Last point I want to make is this. One of the first journalistic pieces I wrote on X, when I first started this, was about what are the implications of aliens being real and us finding some extremely significant technology. Either they are malevolent or benevolent or neutral, right? Either they want to destroy us, they want to help us, or they don't care about us at all. They see us as ants, whatever. In all three scenarios, the logical conclusion the species like us, the lesser species, would do is reverse engineer the technology and try to catch up. It doesn't matter what the scenario is. It's not like it's like, oh, they're benevolent. We don't really need to worry about how to figure out their technology. We'll just let them give us what we're bestowed. No. In all scenarios, you would just try to reverse engineer technology. And what are they lying about? They're lying about that they haven't figured it out. That's what they're lying about. It's the simplest lie. Just say you've never figured it out. People demand proof. So if we just don't give it to them, then no one will ever really believe it. Even if people know, they'll just tell stories. You'll never get academia to believe it. Sadly, that's how easy it is to control a populace. And it's disappointing for the people like Elon Musk, Tucker Carlson, and Joe Rogan that they don't see the same level of disinformation and misinformation that they saw during COVID has always applied to physics for the last 70 years as well. The same thing you saw in medicine where they were just making up imaginary reasons to give people shots. Oh, you got this year's cold virus. Oh, shit, better shut down the world. Give people a bunch of shots. This is the same bullshit nonsense that's been going on in the physics world as well. We have straight up pseudoscience being taught as mainstream physics when it's not really accurate. And we can't even model cosmology. We can't explain the Casimir effect and various other effects that prove quantum mechanics. We can't explain it in the classical view. We have to change our view of the universe. And we have to better understand the laws of physics and how gravity plays a role and is related to electromagnetism. We must understand that and teach that to the younger generation. Hello, hi there, Birdie. Welcome. Okay. Whew. We cooked, chat. Let's just get right into it. Okay, so why attosecond lasers? Why are attosecond lasers important? Well, attosecond lasers are one of the ways where we can produce the balls of plasma that we need. Perhaps not the exact balls of plasma in the MH370 videos, but maybe. Maybe. I happen to believe that there's probably another way that we can do it without lasers, but that it's maybe some way where it's a little bit too close to the sun if we dig into that. Okay. Now, Salvatore Pais has been kind of sitting in the back seat of UFO disclosure for the last 7 years. I helped bring him back into the forefront because I've always believed him, even well before I did this. When I first read those patents, I always thought they were real. Want that to be on the record, even back in like 2018 when I first read them or whatever. And even Lou Elizondo yesterday used one of Sal's patents in an event that he was holding where he was doing a demo or presentation. Used one of his patents. Used his inertial reduction for a transmedium craft patent. And there's 5 of those patents. Now, I've spoken with Sal multiple times, and Sal has said that he knew what was going to happen in the MH370 videos. I think that's about as close as he could probably come without breaking any NDAs to basically saying that those videos got to be real from a scientific perspective. There are 2 videos I want to show you guys right now in terms of why attosecond lasers are important. Okay. And they both feature Salvatore Pais, man of the hour.
Interpreting it correctly, then you're talking about high energy plasmas with basically waveforms applied to them, and that would be enough.
Non-equilibrium plasmas. That's a key factor. Okay. Non-equilibrium. So we're talking about, you can call them cold plasmas. Plasmas that do not obey the Maxwell-Boltzmann distribution of the electrons within them.
Okay.
That gives you an idea. How could these...
If they're not obeying the Maxwell-Boltzmann distribution, that might be the key to amplifying energy beyond where classical physics thinks that it just falls off. Wow. I wonder if that's also what he's saying there.
Plasmas be created? Hint, hint. Attosecond, femtosecond lasers. Among other things, the other easier way to create these.
I don't think Salvatore Pais has ever told a lie. Well, he did lie, I think, when he said he's never seen videos like the MH370 videos. He definitely has. And I think he's definitely seen a UFO or whatever we would call a UFO. I think a normal person off the street would call a UFO. So why do I think that? Well, because did you just listen to what Sal said right there? Said we need to make non-equilibrium cold plasmas, and how do we do that? We use attosecond lasers, and we might be other ways that we can do it as well. He said, "Okay, well, I believe you, sir. I believe you. Are there other ways? Well, whatever. Let's just start with attosecond lasers because that sounds like magic enough. Sounds like Harry Potter's wand. Hold on, let me break out my attosecond wand. Boom. In fact." Somebody out there, if they're playing Harry Potter games, I don't know if you can name your wands, probably. Call your wand Attosecond. There you go. That's a freebie on me. You'll be the coolest, dopest quantum mechanics kid in the Harry Potter universe. Okay. One more Salvatore Pais video, which is very relevant because when we're talking about attosecond lasers, we're shooting photons. We're shooting electromagnetic quantum particles. And so it's like, we want to understand when people ask what is an attosecond laser? That's a very good question. What even is a laser? How does a laser work? What is light? These are all intertangled questions, which I think that generally we don't really understand that well. And so what's nice is that we're going to learn more about what the phenomenon of light even is as we learn about attosecond lasers. And that's why I want to watch the video with you today, because I like to show stuff that I think is educational. Now, a lot of this is going to be pretty deep quantum mechanics stuff, but I'm going to try to do my best to help bring it down to earth. But this is the reason why we're going to watch about attosecond lasers tonight.
Strictly charged superfluid could be a superconductor. So the idea being that it's possible that we can actually slow photons.
What's going on here?
In a superconductor.
Hold on, one more time.
An electrically charged superfluid could be a superconductor. So the idea being that it's possible that we can actually slow photons in a superconductor.
Okay, slow photons in a superconductor, and plasma could be a superconductive liquid circuit. Well, not liquid, but whatever you want to call plasma, I guess. So you just add that up and you say, okay, those 2 videos tell us the MH370 balls are balls of plasma. They're superconductive, and perhaps they might be coherent. They have, they're not dissipating. So that's from the man himself. And that's why we want to look into, okay, well, how does an attosecond laser work? And before I do that, did you know what laser actually stands for? Beep, boop, beep, boop. It stands for light amplification by stimulated emission of radiation. Light amplification by stimulated emission of radiation. When I hear that, it almost sounds itself like amplification of energy. Like, because isn't light energy? Isn't a packet of light just a quantum of electromagnetic energy? Isn't that what light is? Now, let me explain very briefly my perspective. This is just my perspective of the universe, how I envision this video game simulation that we're in, is that I imagine when light occurs, there's a stimulation in the ether, an electromagnetic stimulation in the ether. Now, why do I like this view? This is very non-scientific. When I look at my window and watch the light come in, if I make the room relatively dark and just let the light from the window illuminate the room, it illuminates the whole room. It doesn't act like individual particles. It's acting like a wave, basically filling up the whole room radially. And when I look at that, I think, this feels more like what I would imagine a medium lighting up than necessarily like imagining beams of particles hitting me from the sun, for example. Now, perhaps I'm totally off base on this, possibly could be. But if it is true that we're stimulating the ether, then perhaps there's a way where you can amplify that stimulation effect or create some type of pump into it. And then you could have effects that would be classical physics would think are impossible. So we'll see. Here we go, guys. And thank you guys for watching right now. Let's do it, guys. So tonight, the main course. Oh wait, this one's for later. That's a later stream from some other science. Wait, where's my videos? Oh, here it is. Attosecond lasers, attosecond science, not just laser science. In fact, let me just do these quick super chats. We are the change. Thank you very much, brother. Appreciate you. Rare W for coming. It really is. It really is. Tic Tac Tundra, thank you. Told you're on the right path, bro. Love you, bro. Thank you, Tic Tac Tundra. Love you too, brother. And thank you. Oh, follow-up donation. Corporal's Corner found something hung. I don't know what that means, chat. Someone give me the context on that, chat. Okay. So, here we go. Attosecond science. Wait, I feel like StreamYard's acting weird. There we go. So this is presented by Paul Corkum of University of Ottawa. Electron that is multiphoton ionizes its immediately subject photoionizes is immediately subject to the light's electric field that will control its short-term future. This control enables a gas of atoms to produce intense VUV or soft X-ray beams. Since we can precisely control the infrared beam, we can synthesize attosecond soft X-ray pulses. Pulses that are the shortest controlled events ever systematically produced. For a complex atom, such as xenon, the recollision electron shares its energy in any multi-electron interaction. Measuring the energy share encodes multi-electron dynamics such as femtoresonance structure in helium and the giant plasmon resistance in xenon. Okay, so I don't know if it was these people, but they won the Nobel Prize in 2023 for attosecond lasers, for producing attosecond lasers. So we're going to understand and try to figure out what all of this stuff means. But basically, they are trying to produce the smallest quantas of light that they can from a time perspective. So they're going to explain exactly how it works, actually pretty much right in the beginning here.
Which is 1920. Now, I looked on the website before I prepared my talk, and it said the talk was for undergraduates, partially. And so I decided that I would put a few things in just to make sure that everybody was on the same page. So I don't know how many undergraduates came, I can't see. But I thought I would start out with what is an attosecond, because I come from the joint Attosecond Science Lab. So an attosecond is 10 to the minus 18 seconds, or 1 over 1 with 18 zeros. I like to say you divide a second into a million pieces and you get a microsecond. You divide a microsecond into a million pieces and you get a picosecond. And you divide a picosecond into a million pieces and you get an attosecond. It's nice to contrast it with what, I mean, there's no easy contrast in time and space, but maybe you'd say a meter is like a second. So if you do, nanometers, which is a big thing, nanometer science, is 10 to the minus 9 meters, which is huge compared to attosecond to a second. Even a nuclear diameter.
So basically, it's extremely, extremely, extremely tiny. A millionth of a millionth of a millionth of a second. 10 to the minus 18. Minus 18, if you're not good at math, that means 18 zeros. A period with 18 zeros and then a 1. Very, very small. So if you're wondering, yes, we're getting close at this point to interacting with like quantum things. It's pretty small. Although things get a lot smaller theoretically at the quantum level, but this is pretty dang small. So why is that important? Because it shows humanity is advanced pretty far from a material science perspective if we can do this.
So since we're talking about attoseconds, and I want to end up with multi-electron dynamics, let's look and try to think about what you might expect to happen on an attosecond timescale. So I picked this off the web, and it sort of talks about the natural timescales for gases, really. So an air molecule collides with another air molecule about once every nanosecond. So nanoseconds would be a typical time for collisions in densities of air and temperatures of air. A molecule will rotate, a typical molecule will rotate, in more or less a picosecond. I mean, of course, there are big molecules which are slow, and there are smaller molecules which are relatively fast, but sort of picosecond-ish. A chemical reaction cannot be faster than moving the atoms apart, you might say. In other words, chemistry is really moving atoms. And so it really can't be much faster than a femtosecond just because of the inertia of pulling the atoms apart. So attoseconds is the electron timescale. Electrons move and interact on the attosecond timescale. And so that's the kind of physics that...
Bro, what? Electrons move at the attosecond scale? Look at this. Look at this, chat. Look at it. What are the timescales we're talking about here? This is below everything. They're like any chemical reaction, the fastest it can work is femtoseconds. So we're talking about measuring things at scales beyond that are anything practical other than just energy. So now we're literally talking about interacting with electrons directly. Interacting with electrons directly. Now, if I were to come up with what are the ways where we can begin to engineer reality, I'd say, well, the first thing we need to be able to do is interact with the electrons directly. Interacting with the electrons directly is like, wow, that feels like if there is ways to cheat physics, like now you can engineer reality. Because what are we even made of? Everything's made of atoms, which is just with like, an ion is a molecule missing its electron. It's not equal. And, if you're starting to manipulate that, it feels like you should be able to manipulate the quantum effects at the macroscopic scale now. Like this is a tool. This is a tool to bring the quantum effects up to the macroscopic level. If you really think outside the box on what this means, isn't it? I just can't get over this graph. Basically saying this is just beyond anything. like rotating atoms and stuff like this, like atoms colliding or not colliding. This is all beyond those scales, like significantly.
That will be opened up with attoseconds. In a way, if you wish to make an attosecond pulse, you must deal with electrons. So I called this, I think I called it when I put the advertisement in for this, attosecond science. But I sometimes call such talks using light to control electrons, which in turn controls new light. This is much more general than what we do in attoseconds, but it's a good way to introduce attoseconds. So think of an atom, which is illustrated here, and think of electrons in the atom, illustrated right here as classical particles. Of course, you all know they're not. And think of an intense laser field or a laser oscillation. I'll simply follow one cycle of that oscillation. And when the laser field is strong enough, then the pull on the electron is great enough that the electron will emerge from the atom and go into the continuum. So it will come out somewhere near the peak of the field. If you want to think of it quantum mechanically, the electron you can think of as tunnels. But if you want to think of it classically, you're just pulling it. Eventually, you pull stronger than the ion pulls back. Once free, the electron gains momentum.
Okay, so if you're already lost, what is a laser? So when they shoot a laser beam, they're shooting one wavelength of light. So when he's drawn that wave like that, that's literally what a laser is doing. That's why lasers are one color. If you didn't know that, that's why a laser will be whatever color, because it's shooting one particular wavelength. So when it's shooting this wavelength of light, it's producing an electromagnetic field based on the right-hand rule. And so what he's saying here is that we can potentially use this to interact with gas or whatever we want to interact with. Like a gas is just a bunch of molecules, right? Xenon gas, helium or hydrogen gas, whatever it might be. And we can use the laser to interact with the electrons in that gas. So if you just take a simple example like a hydrogen, we've got our hydrogen atom that has one electron on it. What are we going to do with that electron? Well, if you've been following this live stream, you probably have a really good idea. We're going to rip it off and create a plasma, right? We shoot an electron, we shoot a beam of attosecond beam in there. We can rip off the electron from its orbital, from the orbital of the nucleus.
In the presence of this relatively intense light field, pulling away from the ion from which it originated, gaining momentum, and that momentum pushes it uphill against the field, which now is pointing backwards. And depending on its moment of birth, in this phase back here, its moment of birth, it can come back and collide with the ion from which it left. The illustration shows one electron hitting another and knocking it free, and this happens. But what is really driven attosecond science is something a little different. The electron comes back and falls back in and is captured into the state from which it left, giving off its light as a photon, giving off its energy, rather, as light as a photon. You might think of this classically as the electron, which is being driven by the laser field at the frequency of the laser field, sees the Coulomb potential, falls in and out, and has a high frequency emission. And that would be a classical analog to what really happens quantum mechanically, which is the electron recombines.
What, like, is anyone out, like, am I tripping, or is anybody else just thinking fusion bombs right now? Like, I feel like I'm just thinking fusion bombs. So what did he just say right there? Let me just break it down. How does this work? Like making the attosecond laser, if I'm understanding correctly so far, physical space is the gas. So we're shooting this laser through a gas, and it's ripping the electrons off of the molecules in the gas. But then the electrons, because the wave changes phase. So when the wave is going one direction, the electron rips off this way. But when the phase changes, it comes back. So the electron temporarily rips off and then comes back and hits the ion that it was ripped off from, releases energy. Oh boy. So Isn't that just fusion? Isn't that the concept of fusion? And now I'm wondering, what's the relationship between a laser and gravity? And what would it take to get lasers to manipulate gravity? Let's keep going. I feel like, just truthfully, chat, I've already watched this whole thing once. I feel like I have to watch it like 10 times. This video humbled me, which isn't too surprising since I'm a non-classically trained physicist. But I watched this and I'm like, I need to make sure I understand exactly what this guy is saying, because the true reason why we're watching this is there's several analogs, in this video to the MH370 videos. Like, I feel like whatever was done to make the plasma balls or make the plane disappear is the same physics and science that we're watching on how to produce attosecond lasers themselves. Like, somehow figuring out how to make the tool actually teaches you how to make teleportation. That's why in the thumbnail you saw plasma and teleportation, because it looks like the tool unlocks the science, which I could never have thought, oh, we're going to read about attosecond lasers and be like, why is all this so similar to like the orbs and everything that we've got going on? Let's keep going.
Process that I've talked to you about, which seems so classical and so simple and things like that, can be made quantum mechanical, but I will do it a little later on, but it will still be simple. And it happens pretty well in all materials under strong fields. I might state this in semiconductor or solid state language, just because I know a lot of people are in solid state. And we can transfer it into solid state, and much the same process happens. So let me say it in solid state language, where we have energy and momentum. An electron is created by a band-to-band transition from the ion, which has a very large mass, and therefore has essentially energy versus momentum, which is flat, up to electron, which has a much lower mass and has an energy versus momentum, which is parabolic. The electron now is accelerated on its band, its parabolic band, until the electron and ion find each other, which is not now illustrated in this illustration.
Oh, no, they find it.
And then they make a transition back to the ground state from which it left. The electron and ion recombine, giving off radiation as a photon. That's just the same thing as I talked about over here, but I'm talking about it in solid state language. And indeed, exactly this process happens in a solid. But I won't talk about solids here. I'm really talking only about atoms and molecules. So just to make sure that that's absolutely clear to you, a moment of birth, illustrated here by a moment of birth in the field, is mapped into a moment of recollision by F equals ma and an energy of recollision. I illustrate by red, green, and blue, and I've illustrated that by some arbitrary number. It depends on the field and the wavelength, but the recolliding electron could easily be 100 electron volts of energy when it recollides back with its parent ion. And if it's 100 electron volts of energy in this trajectory, if it was born a little bit later, it will have a lower kinetic energy, 50 electron volts, let's say. Again, this is arbitrary, I made it up, but this is the way it works.
Wait, what? Am I understanding this correctly? Is that depending on the wavelength of light that you use in the process, you're going to get different an energy release, and the energy release is significantly different, like 10 times higher, looks like here, between red and blue? I think that's what he's saying here, because he's saying basically like wherever the phase hits, it's going to have, when the electron rips off and bounces back, the amount of energy released is going to differ. So the only variable I can imagine here is the wavelength, right? Or am I missing something? Or maybe it's like a matter of getting it in phase. I'm not sure. Matter of getting it in phase would be like shifting it like this. That's getting it in phase. Wavelength would be stretching it out. You can't really do much with waves, but you can do those two things. Yes, blue is definitely more energy, but why? Why is it? That's what I don't really understand. I mean, obviously, it must have to do with how the electron got ripped off and its energy coming back. It's coming back with more energy, right? Huh. I'm sure that somebody in the chat and the description today, I'm going to need my PhD physicists who are more red-pilled than the academics to help us out in the comments later on.
And it's still later birth will lead to an earlier recollision in the lower energy. So we have a sweep of energy from red to green to blue, a bit like taking a short pulse through a material, and the material will disperse it. So if I take a short pulse through tin, the mirror especially of this wavelength, it will be dispersed. And what I'm doing is just doing the opposite. I'm taking the red, the green, the blue, and put it through tin, and I make it back again. So this process that I've described to you earlier produces a chirped pulse, red, green, blue, and when you pass it through a dispersive material, in this case tin, remember it's UV, so solids can be transparent or relatively transparent to this material, to this radiation. You can create an attosecond pulse. And indeed, this is exactly how attosecond pulses are created, even the tin.
Okay, so what is a chirped pulse? A chirped pulse is a pulse of light or other electromagnetic radiation where the frequency changes over time, meaning the instantaneous frequency of the pulse increases or decreases during its duration, essentially chirping like a bird. This is often achieved by manipulating the phase of the wave to create a frequency sweep within the pulse itself. I don't know if that helped me understand it a lot more. Okay.
Now, I don't know, again, if any undergraduates really...
Okay, so then he puts this, if you're interested in this math equation here, I'm not sure if this is meant to be like you're meant to figure out something from this. I don't know if it's a trick question or what have you. I actually asked the AI this, but the AI couldn't really understand the implications of what he meant between the phases. If he was trying to get at resonance, I think that he might be trying to allude to some resonance effect here. But he gives a math scenario here. You guys can check it out on your own. If you want to answer it and explain the answer to this in the comments, I'd love it, because in the original video, there's no answer to this question.
Cycle or a cycle and a half.
Hold on, let's back up a little bit.
Well, it's controlling light to control the electron to make new light. So controlling light will make a time dependent.
So controlling light. Why would we do this? Why would we do this, Chad? We're controlling light to make new light. If the world was black and white and everything was based on classical physics, this would be pointless. Classical physics would say you could never get more energy out of your light production here that you're doing. So the original laser should never be able to produce more light than the original laser did. But I guess maybe you're figuring out a way to like change the frequencies or something and change the light that's given off. Weird. Anyway, let's keep going.
Dependent laser pulse, who is perfectly controlled. And the simplest way to think of it is, let's make a pulse that's only a cycle or a cycle and a half long. Over here on the right-hand side, you see the square of a time-dependent field of a pulse that we can produce, which is even less than a cycle long. It's even half a cycle long. So that can be done, and people can make pulses that are a cycle or a few cycles long.
So
now let's think about
the one on the right is femtoseconds. You can see FS down there and the blue on the right, and it's squared. So that's the reason why you don't see the ups and the downs like you do on the one on the left. So that's why all the ones look like peaks, but some of them phases would be inverted.
About it. Here, the intensity isn't strong enough to remove an electron. Let's make it so the intensity is also not strong enough to remove an electron around this peak. But by this peak, maybe the intensity is strong enough to remove an electron with some probability. The electron is caught in the increasing field, driven away, driven back, and recollides with high energy, creating that burst of radiation that I described to you with all of the descriptions, the chirp and everything is not shown. Now you're going to say, okay, but the next...
That's how they make an attosecond pulse. There it is right there. Just figured it out. How do they make an attosecond pulse? Well, the answer is we can't make one naturally, so we're going to engineer an attosecond pulse. We can engineer an attosecond pulse by forcing the electron to rip free at the exact energy levels using the correct medium of gas, so that the pulse, so that when the electron comes back and hits the ion, it releases the exact amount of light for an attosecond pulse. Boom! Check it off the list. We understand attosecond lasers and how they made it and why they won a Nobel Prize for this. I'm going to have to do a separate entire video about this now that we actually understand exactly why they won the Nobel Prize, because this is awesome. Of course they won the Nobel Prize for this. This is awesome. They're using a laser and they're just using straight up math to figure out exactly how much energy is supposed to be released. They're figuring out how they can make a chirp pulse, an attosecond pulse. And so that's what you see here is the part that he's got circled. This part that's being circled is the energy that's being released after the electron breaks free and comes back and hits the ion. That's what you're seeing. And so you're seeing the chirp pulse. That's what he just said. So now that I've given you that context, listen to the last 20 seconds.
Electron is caught in the increasing field, driven away, driven back, and recollides with high energy, creating that burst of radiation that I described to you with all of the descriptions, the chirp and everything that's not shown. Now you're going to say, okay, but the next half cycle is even stronger. The atom is more likely to ionize. And so that electron will also be created, or it will have a probability of being created, and it will be pulled away by a strong field. But it will be driven back by an increasingly weakening field, and it will come back, and maybe it will recollide, but it will recollide with much lower energy, and therefore
that's why there's going to be
a much less high frequency burst of radiation.
That's why there's going to be a chirped pulse. Holy fucking shit, chat. We're learning quantum mechanics right now. Let Professor Forbes step up to the plate here. So what does quantum mechanics tell us? Everything is based on probability. So now I know the answer to the question that he was asking earlier, is that what he was trying to point out is that when we're looking at this phase here, this bottom left one, let's say there's a 25% chance that an electron breaks free. 25% of the time, electrons are going to break free. Now that is just straight up going to be a lot of the universe. There's 100 electrons, 25 of them are going to break free. Now that one, the top peak up here, what if that one, there's 50% chance the electrons break free, but there's also some percentage chance the electrons that broke free from before are recolliding. This causes these electrons to recollide, but at the same time, some of the more electrons break free at the same time. And then the third peak, and this is just one phase, right? So this pattern would be repeated over and over and over and over and over again. What happens with the third peak? The third peak down at the bottom, some of these recombine, some of these other ones recombine in the second peak, and more break free on the third peak. But the problem is because the intensity of these peaks are different, we're going to see a chirped pulse. We're going to see one frequency up here, and we're going to see a different frequency down here. We're going to see two different frequencies get released. That's why he was saying we're going to see the multiple different bands of energy levels of light get released, I think. Yeah, so now we're seeing what do we understand is really happening here? What are we really talking about? We're talking about shooting an electromagnetic pulse, light, laser, into a gas and producing a plasma. Why? What is a plasma? A plasma is the electrons breaking free. He's talking about producing plasma. On short time scales, they're recolliding, but it's still producing a plasma. And if that laser's on, then it's going to continually produce that plasma. And that combination is going to keep happening. And then what do we have to do? All we have to do after that is manipulate the phase of the wave. The wave, or not the phase, but the wavelength. What frequency do we want to hit it with? Because the output's going to be dependent on the frequency we hit it with. And probably the medium that we use. What kind of gas are we going to use?
Filter, and just looking at the highest frequencies, one gets.
Ooh, hold on, chat. Ooh, first of all, let me just hit up these donos real quick. I feel a rant coming on, chat. Ooh, I feel a rant. Happy Monday, Yahtzee, Mark Scott. Thank you very much, brother. Feel a rant. Nobu, thoughts on how to put up ultra terrestrials, not ultra dimensional, ultra terrestrial models. Really good paper. Definitely check it out. Why is he writing that paper? He probably knows. He's probably right. Read that paper. Ultra terrestrial models. We have the change. Thank you. Is it possible each orb has some kind of attosecond laser? Yes, it's possible to have something like an attosecond laser or equivalent tool at their disposal. Absolutely, I think it is. Thank you. We are the change. 1 Tundra, we can vaporize a 5-mile radius on the ground. Well, okay, let's chill. Let's chill. 1 laser target bathes in ionized radiation. 2 lasers is the okay. Well, let's keep it, you know, family friendly here. Now that you said that, okay, you damn spooks that are listening, we are getting really close to being able to produce some pretty scary stuff here. I mean, if my hypothesis is correct about this, then this is basically going to be a secret and a way to open the door to cold fusion and potentially a huge amount of energy. And maybe we do require some secret sauce at Sal's saying beyond attosecond lasers, but boy, we are getting close. We're getting really close to understanding the actual quantum mechanics and the math around it. So this is going to produce recollisions. And what if then it's just a matter of, oh boy, now, oh shit, chat. Man, chat, Yahtzee moments are coming at me hot. I did not expect this. Oh my God. Why did it all just hit me all of a sudden? It just hit me. So the question is, when we're looking at this, so what do we want to do now? So we've created this chirped pulse. Well, what if I don't want a chirped pulse? What if I don't want a chirped pulse at all? What if I want to keep my ions and electrons separate? What if I don't want them to recombine? What if I don't want them to recombine at all? Then what do I do? And what if I want to change the type of interaction that I want? Well, the answer is I'm going to manipulate this wave. I feel like what happens if I have a standing wave? How do I produce a standing wave, actually? That's really the question. Isn't that what I want? I want a standing wave that's going to keep things stabilized. That's what I want in the MH370 videos. So I think this might be similar or close, but not exactly it. Because that's not a standing wave. That's producing a chirped pulse. Somebody brought up optical tweezing. You know what? Because you just reminded me of this, and I was totally gonna forget. Here you go.
See that when I put this ball in water, the water sticks to the surface of the ball and causes the water to change directions and shoot the other way. And the result of that change direction is that the ball is forced towards the center of the water. It's forced into the water. Now this same thing actually happens with a particle when it's in a light beam. So if you want to lock it in place in 3 dimensions, then all you do is you focus that beam down to a center point. Now what we need to do is to be able to generate a particle right near that focal point of light that's small enough that can be pulled inside of it. In order to do that, I'm just going to be using a Bic marker here. Oh, right there. Got one. I got one. No way. Look, we got it. Don't move. It's caught in there. The particle's actually floating in the air with light. So it's actually trapped in the laser beam here. You can see that bright spot right in front of it. That is amazing. It actually works.
Trapped in the laser beam? Okay, the more I'm looking at that, the more I'm going, okay, so you can definitely just trap plasma in a sphere. Why would we not be able to? Look at what we're staring at right there. It's trapped in a laser beam. Isn't a laser beam just energy? Yeah, of course it is, but it's emitting electromagnetic radiation, right? Or it is electromagnetic radiation. Wow, that is crazy. I'm gonna have to play that later on my X channel.
You can see it can be pulled inside of it. In order to do that, I'm just going to be using a Bic marker here. Oh, right there. Got one.
Yeah, the more I'm looking at this, the more I'm like...
No way. Look, we got it. Don't move. It's caught in there.
It's right there.
The particle's actually floating in the air with light. So it's actually trapped in the laser beam here. You can see that bright spot right in front of it.
What would you call that? I would call that anti-gravity, right? Anti-gravity. Although in this case, the particle is so light, the electromagnetic forces can probably just keep it aloft. But isn't that what anti-gravity is? Isn't that what anti-gravity is? If light is just coming from the ether, then couldn't the ether of energy be explaining why we're seeing gravity at all? Definitely think there's a connection there. Okay, let's keep going. Got some more stuff I want to look at. Before presenting, remove other media. Okay.
It's an isolated attosecond pulse. It's chirp, and we put it through a material like tin to fix it. But otherwise, that's it. So what's down here is just the equation for what energy you can get, and it depends upon the field that you're pulling it away with, or the field that the atom ionizes. It depends on the frequency of the laser that you're driving. And that's really all there is to it. It's really quite simple.
So the energy basically just depends on the frequency of the laser you're using to drive it. And if I'm doing my math correctly here, looking at this, you're dividing by frequency squared. So I would want my frequency to be very low. Is that true, chat? Because it seems seems to counter the idea of high frequency. Wait. Yeah, frequency squared. Maybe I don't understand something. Oh, is that wavelength and not frequency? Maybe that's why. 1 undivided by, okay.
So one can drive with 800 nanometer lasers up to around 150 EV. I said 200 EV in a high IP atom like helium. Helium is not ideal, mostly neon is used. And you can go up to high IP at 800 nanometers. And if you want to go up higher to a kilovolt, which people do, people can go to a kilovolt attosecond pulse or kilovolt high harmonics, then you have to push the wavelength of the light longer and longer. And so that's the way. Okay. Now,
yeah, longer
I have not told you everything. I've only told you as if it's a single atom being irradiated by a beam. I have told you that all of the complexity is out here in the laser, which is not shown. We have to make almost a single cycle pulse if we want an attosecond pulse. But if we take an ordinary garden variety Ti-sapphire laser, we'll have an attosecond pulse, followed by an attosecond pulse, followed by another, followed by another. Fourier transform it, it's a series of harmonics.
Series of harmonics? And Sal told us about sapphire lasers. Said you just get a sapphire laser. We've known about this sapphire titanium laser or something like that. You can buy them; they're just thousands and thousands of dollars. And what are you going to do with it? I mean, you don't have like a vacuum chamber to test it, and you're going to just find stuff that people already found anyway. Now, this is pretty interesting. Harmonics and resonance are definitely connected to this. Definitely connected to this.
Harmonics 15, 17, 19, 21, 23, 24, etc. And this is the typical harmonics created by a typical femtosecond laser pulse irradiating argon, or maybe neon. This is argon, I'm pretty sure. If I isolate it, as I told you before, here is the spectrum going out further. You can see it not only 35 eV, but it's on the same scale, approximately the same scale, continuously. In the vertical direction, I forgot to say, there was no information. It was just a spectrograph, so you see a spectral line.
So that's just a spectral gas, what the gas looks like
spatial structure of the beam.
When the lights
are this is telling you about the spatial structure of the attosecond pulse, but roughly it's a continuous spectrum pushing all the way out to well over 100 EV. Okay, so that's high harmonic generation. In reality, it's not very complicated. All the complexity is out here in the laser, and if you want to do this, you can just go buy such a laser, a commercial laser, put together a vacuum system. A supersonic jet, that's what we use here in Ottawa mostly, but it can be a fiber holding gas, it can be a cell holding gas, and nowadays it can be a dielectric, although you cannot push to such short wavelengths, but you can push to 25 EV using a solid material.
Oh, so they are trying to go for shorter wavelengths. Yeah, that makes more sense. It should be shorter wavelengths, right? Higher frequency. This is going to get really interesting here. Let me see here. Okay.
So now I've described to you creating an attosecond pulse, and I hope you will not forget it. I don't think you will. will ever forget it. And if you go through the calculation I asked you to do as undergraduates and you get it, you will have it in your fingertips and you will never forget it. And it's easiest to describe it by thinking about a conventional street camera, which maybe nobody in the audience here has ever really looked at or thought about. So let me describe a conventional street camera. This is the technology of the 1960s, I guess, or 50s, when it was difficult to make measurements of short length.
Technology of the 50s or 60s.
So you brought a pulse in to be measured into a photocathode. And in the photocathode, the idea is you make a photoelectron replica of the pulse that you wish to see. Now, of course, you make the photoelectrons out of the solid. They got to make their way out of the solid. So the energy is not a perfect replica. They can lose some energy in the process and so on. But you make the best replica you can make on the photocathode. Now you pull the electrons as fast as you can up to between two deflection plates on which you place a high voltage time-dependent field, just like a television, old-fashioned television set. And so the first electrons that come in, they see one field and are deflected over here. And the later electrons that come in see a different field and they're deflected over here. And so you create a streak across a screen, a fluorescent screen, that is a streak showing you the structure of the pulse. That's a street camera. Street cameras like that.
Okay, chat. I feel like I am just what? You know what? I'm just going all in on this. It looks like he's just explaining teleportation in the MH370 videos when I watch that. When he says, figure out what pulse, you're going to do a recreate your pulse. I imagine recreating the plane. Imagine the plane is a wave, and you're going to recreate that wave. So what are you going to do? You're going to shoot it through your time-varying high voltage. What's your time-varying high voltage? That's your orbs. That's your 3 orbs. That's exactly what the orbs are. The orbs are time-varying high voltage. That's what the ball lightning is. And then what are you doing? When you're shooting it through there, you're fucking teleporting it. You're teleporting it. You're forcing it to a specific direction through the high voltage. And so that's what they're doing. They're manipulating the direction of it on the end of the plane here. And you're seeing it, in this case, get pulled to the left. Now take this to its extreme. And don't imagine it just getting pulled. Like it's literally ripping through space-time. And then that slingshot effect that I always talk about, if you took it to its super extreme, that's what you would be seeing happen here between these two plates. It's distorting space-time itself because the voltage is so high. And this is actually extremely similar to Google 4-wave mix pumping. 4-wave mix pumping. And you can use, you don't have to be just like, basically they take 2 waves that are 180 degrees out of phase. And then you shoot another beam into it and it reflects, like phase conjugate reflects back. For some reason, there's like a really weird connection to this between quantum teleportation, double slit experiment, and experiments like this are all really, really similar.
That are still used for measuring X-rays, and they've really improved considerably. I think they can now have a time resolution of less than a picosecond, maybe 100 femtoseconds even, I don't know. But otherwise, except for here and there, they're essentially unused. But you could think about how you could improve such a street camera. So one problem is the photocathode. So let's get rid of the photocathode. Let's replace the photocathode with an atom. So now I come along, I just ionize, and I create.
Replace the photocathode with an atom? With atoms? You mean like an object? Okay, let's replace the photocathode with an object. What else should we do? Let's go full screen for this.
Create a photoelectron up here. Let's take the hydrogen atom to make it easy. I create a photoelectron. Its energy range is exactly the energy range of the pulse. Its time structure is the same. As long as I have a simple enough atom, I create a true photoelectron replica of the pulse. So that's the first thing, and that would improve the street camera dramatically. The second thing.
So the first thing would be you would need to figure out the exact pulse you need for the plane, for whatever object you're going to manipulate. So the orbs are probably mapping the plane. They're mapping the plane. They're figuring out exactly what the pulse needs to be because it's got to be perfect.
It's going to use an atom. Why put it over here? Why not stick it right in the middle of the deflection plates?
Yes.
And so we'll put it right.
Why not stick the atom in the middle of the deflection plates? Yes. Yes. Why not stick it right in the middle of the deflection plates, chat? And what would happen if you squeeze the deflection plates onto the atom? That's what I want to know. Ooh. Just feels like we're close. Why does this not want to leave? Oh, there we go. What the hell?
Right in there in the first place. And then why use deflection plates? Why not replace the time-dependent field with an infrared laser pulse? Laser pulse gives you a time-varying field. It's just faster, but that's great.
Replace the time-varying field with an infrared laser pulse. Who was it in the chat earlier that said the orbs might have a laser on them? Yes, you are probably right. This is why, guys, I've been saying for a long time, the orbs almost certainly have some kind of laser, negative energy laser. It might be a tunable laser that can do multi-purpose, like a Swiss Army knife type laser that they have. Can it manipulate gravity? Yes, absolutely. We just watched an object being lifted in a laser pulse. And you would say, well, Ashton, how can this ball of plasma float? Well, because the ball of plasma isn't very heavy. It doesn't have a lot of mass. So it can easily float. So that might be another reason. Like, I don't think we're breaking any laws of physics at all. We're not breaking any laws of physics with this, with anti-gravity. Because once again, the whole gimmick of anti-gravity is that gravity is not some elusive particle that we can't find. Gravity is just a pressure force. So how do you counteract a pressure force? A different pressure in the other direction. That's it. That's it.
An attosecond pulse. And then the last part we generally use, we take the measurement in energy instead of streaking it across the camera, across a fluorescent screen. But that's sort of either way would be fine, I guess. So the attosecond streak camera replaces the photocathode with atom, replaces the time-dependent field with an infrared field from a laser, and that's the deflection. So that's the best way to measure attosecond pulses. In fact, what you measure is something. Oh, this is actually how such a measurement goes. So let me talk about that first.
So they shoot the beam into the gas of argon. That's what they're using here. Argon gas.
In Munich. A short pulse comes in and creates the attosecond pulse. The attosecond pulse now propagates along with the short pulse, and it's separated from the driving pulse by a set of apertures, now creating an infrared beam, which will do the deflection, and the attosecond pulse that comes through here is the.
You fucking spooks who've been hiding those MH370 videos. Oh my God, your reckoning is coming. It's going to be such a beautiful goddamn day. You have no idea how joyous a day it's going to be. I don't like to play games, so let's just get right to it. Read the DIRD that I've been talking about, Defense Intelligence Reference Documents, about when they're talking about producing negative energy laser. One of the things they talk about is breaking out the negative energy portion of the laser from the positive energy portion. This is exactly how it's done. I've been wondering, how do they do it? Like, okay, sure, you have your gas and you shoot your beam through your gas, but you must use some kind of filter. Yes, you do. Look at all these lenses they can set up on it. You set up the lenses on the beam that comes out, and now you can actually like strip out certain wavelengths of it in different ways. And so now you could send those in different directions. In this case, they're sending them back together, but you don't need to do that. You don't need to do that. That's just an optional thing. If you want to produce fusion, you could shoot them back together. If you don't want to, separate them. These are very physical. How physical are these beams? Extremely physical. Physical in the sense that they are absolutely producing energy. Absolutely no question. That's the whole point of why this won the Nobel Prize. We're reviewing this because this won the Nobel Prize like 2 years ago.
UV. And they come to a second jet, a neon jet, And in the neon jet, we do exactly what I told you for the attosecond street camera, and we measure the energy of the electrons that are created in a time of flight setup. So that's the attosecond street camera. And so now I think I can sum up this part, the production and creation. So summing up, solving F equals ma, isn't it amazing how simple? The intensity which an atom ionizes, actually I didn't make that case, but you could calculate ionization classically, and you'd be.
So when he's talking about the intensity at which a gas ionizes, he's saying this is the energy you need to make the hydrogen's electron rip off of it. We can calculate that. So we know how much energy it take to get the hydrogen's electron to rip off of it and produce a plasma. We know that. We can figure that out. Just straight up math. Easy math. F equals ma.
Almost exactly right. Because when you tunnel in femtoseconds, it's not much different than classical ionization. So it's the intensity at which an atom ionizes, the frequency and time structure of an attosecond pulse, how attosecond pulses are measured. Isn't it disappointing that classical physics is so good? So which now comes back and interferes with itself into the continuum. Exactly the same problem.
Okay, so here he's explaining, I'm going to skip through this a little bit, but he's explaining the same thing where the electron breaks free. And then you see this one phase at the bottom. So the blue squiggly lines. You're seeing these small phases here where the different, that when we were looking at that phase, phase wave before, you're seeing the smaller amplitudes versus the larger amplitudes. And therefore you're seeing this chirped pulse here. Now this part I thought was really interesting as well. So this is the interferometer, what the interferometer looks like. Let's start right about here.
And you can think about using it in multiple different ways. Okay, so reading that interferometer, because that's really an interferometer, or creating the attosecond pulse is really illustrated in this illustration. The recollision electron, shown here like a washboard, and the bound electron, you can imagine the Gaussian there, they overlap and they interfere, creating that interference. And that interference, there's a minimum here that overlaps the Gaussian, pulls this down. There's a maximum here that overlaps the Gaussian, pulls that up. Square it, and we find the charges on one side of the atom or molecule. It will be true in solids. And as the wave packet moves forward, where there was once a minimum, now there's a maximum. And where there was once a maximum, there's now a minimum. And so the charge has moved sideways. So we have this oscillating charge as the wave packet moves through, and an oscillating charge emits radiation. The amplitude and phase of the recollision electron are transferred through the light through the transition, the dipole moment, or the transition moment. I just described a dipole moment here and how you get it, but that's the transition moment.
Dipole moment? So the dipole moment would be when the electron broke free from the ion, from the molecule, presumably. Is that what, guys, someone fact check me? This is just, I'm trying my best. So a dipole moment, a dipole is when you have a separation from non-neutrality of electric charge. So a separation of electric charge. So if we break the electron away from the molecule, now we have a separation from electron charge. I guess that's a dipole moment, but the electron comes back. So now the dipole moment is over. So the dipole moment would be while the electron is separated away before it comes back. Presumably that's the dipole moment. And so what he's saying here is that we can visually see that dipole moment in the interferometer in the test. So if we do an interferometer, which is the Michelson-Morley experiment, we can see the distortion of, I would argue, space-time from the light being produced from this. Now, why is that big? Why indeed? Well, it reminds me of something else that we looked at once before by Harold Sonny White when he was showing us his warp drive metric, and he was using the interferometer to measure the intensity of the manipulation of space-time. Which makes me think that we are like borderline on the same science and physics that's governing attosecond lasers very possibly governs warp drive mechanics as well. No wonder there's a connection. No wonder plasma is connected to all of this, right? No wonder plasma is connected to this. We're like borderlining on, making a warp drive ourselves at this point. We'll figure it out eventually, chat. We're close. I feel like we're close.
From a point of view of a projectile, the electron is a short wavelength projectile. If you think about using a photon of the same energy,
skip ahead a little bit.
So
here's your interferometer, right? This is what interferometer is if you don't know what an interferometer looks like. So interferometer splits the beams, and what you're trying to do in interferometer is actually quite simple. You're sending your beams 2 different directions, and you want to see if they reach the destination at the same time. That's it. That's all we want to see. If there's a phase change, then they're not going to hit at the same time. So we can tell if there's some interference or something happening, right? That's how we also test for the ether.
But in order to do it,
the problem is we didn't find it because the ether is homogeneously spread all around us.
I want to say that we measure E.
Like searching for water in the water when you don't know water exists. Of course, you're not going to find and realize that, oh, you're in it all the time.
As a function of T.
No, I'm in
or
nothing.
Less often, but we could have done so. E is a function of F with a sheared nonlinear interferometer. I took a picture off the internet of an autocorrelator.
Okay, let's keep
going. Pulse is brought in. So I'm not going to bother I won't show you that here. Put your criticisms, and I'll try to prepare it and fight them back at the
Okay.
Going to change.
This is the part.
Not too warm. Hopefully they're quite cool, about 20 degrees Kelvin. They won't be fully cooled. It would even be cooler if we come down further, but we need a reasonable density of molecules in order to produce harmonics. We'll take a pump pulse that's small in size. That's the orange one. It will be focused, therefore, weakly to large in size here. So we align all molecules. Maybe I should make it clear why the alignment works. Think of this as the molecules, and I have a laser field pointing up and down, and I'm pulling the electrons, and I give it a little twist this way when the field is pointing this way. But as the field changes, the electrons internally sort of bias the other way, and it still pulls it towards an alignment. And so molecules are pulled towards an alignment with an intense laser field, creating a rotational wave packet, a bit like a pendulum. And all pendula align, and as long as the angle's not too great, align at a certain time delay afterwards, and molecules are no different.
What? Did he just explain how you can basically turn atoms back into a wave function? Okay, so here's the rub. So we need our molecules to begin to become superconductive. And why? Because anything, when it's superconductive, then it's going to have this quantum property where it behaves as one. Really, when you actually, if you boil down, this is going to be a good clip probably, maybe not. When you boil down, what does it mean to see quantum effects at the macroscopic scale? The way I imagine it is getting multiple things to act as one. Huh. What does Ashton mean by that? It means that generally when we look at superfluidity, superconductivity, we start like superconductivity, they call it Cooper pairs, because the individual electrons they claim are get paired, they begin to act as like one and then just begin to float through stuff. In superfluidity, the whole blob of the superfluid begins to behave as one solid mass as opposed to individualistic anymore. So if that's the reality, then what if what we're doing conceptually with the airplane and the MH370 videos is we're making one electron, one giant electron, or one giant, maybe the balls of plasma are basically just one massive molecule. It's like one massive molecule that they created on the macroscopic scale. And they're just basically, as Roy D. Herbert said, tricking nature. They're tricking nature into thinking that they're creating one massive electron. What if an electron, because of its weird quantum nature, what if an electron can be any size? What if the one electron theory is true and an electron is more mystical than we think, and that an electron isn't bound to be in a specific size, that the electron can grow and scale up? as weird as that might sound. And then if you do that, now you can cause all the effects you would see in an electron at the quantum scale at the macroscopic scale, including one of the ones that we see the most, which is quantum teleportation, quantum entanglement, non-locality, quantum tunneling. Pretty weird thought, but this video really made me think about it more. I'm starting to think, because when he explains entangling these particles together into like a superfluid, that's using this high-powered laser. Isn't that what we would argue that they're doing to the plane? They're basically turning the plane into a superfluid, turning it into a wave function. So let me repeat the last 20 seconds.
And so molecules are pulled towards an alignment with an intense laser field, creating a rotational wave packet, a bit like a pendulum. And all pendula align, and as long as the angle is not too great, align at a certain time delay afterwards, and molecules are no different. So I mean,
yeah, this is definitely what they're doing. 100%. They're definitely slingshotting the plane. There's a fourth orb. I'm pretty sure there's a fourth orb. They're making the field between the fourth orb and the 3 orbs, just like the Bob Lazar video. That's how they're doing it. So you imagine, just like in this image right here, imagine that space-time that's being bent together like that. And what's happening is they're pulling the distant location forward close to them.
So
wait, that's
Jeremy
the right one.
Reese in
Shit. This one?
Bottom side of the disk are the 3 gravity generators. When they want to travel to a distant point, the disk turns on its side. The 3 gravity generators produce a gravitational beam. What they do is they converge the 3 gravity generators onto a point and use that as a focal point. Then they essentially bring them up to power and pull that point towards the disk.
Yeah.
The disk itself will attach onto that point and snap back as they release space back to that point. Now, all this happens in the distortion of time, so time is not incrementing. So the speed is essentially infinite.
Time is not incrementing, because that's what they're doing here. Oh, well, let's just... That's a really great image right there. That's exactly what's happening. They're just shortening the distance between the 4th orb and the 3 orbs. That's how you have to logically think about it, because that's, from a time perspective, that's what's happening. Instantaneous transmission. Faster than light speed from our perspective, from the outside perspective.
I turn off my laser pulse by the time they're aligned, and then they're just going to go through this kind of quantum mechanical process again and be aligned again. So I'm going to pick one of the revivals later on when all the molecules are aligned. And I'm going to bring in the second pulse, a probe pulse. It's shorter, more intense, and its purpose is to ionize and create high harmonic radiation. And the high harmonic radiation, we're going to look at a microchannel plate, and I think I told you about that. So it's going to be much the same as what I've described to you already.
Oh,
so here's the normalized harmonic intensities. Harmonic number along here, that is the wavelength of the electron, essentially. Harmonic number along.
So they've basically figured out, like, they're just basically way ahead of what this guy's saying. And they've figured out, like, the exact gases needed, the exact energy levels, and the pump, beam that you're using. They figured out all of that. And they've just taken it to, like, a next level where they've figured out teleportation. Like, they figured out that when they started playing with this, they started making things disappear. When they started playing with it. And so they just started taking it to its logical extreme. Next thing you know, they're beaming a Coke can from one room to the next. And then after that, they say, well, how big can we make it? If we can make a Coke can disappear, can we make a plane disappear? Yes, we can. Yes, we can, sirs.
Here, harmonic intensity in the vertical direction. From nitrogen of different alignments. And here's the alignments. You can see that there's a whole set of them, 5-degree intervals. And it's really not important for a lot of time, but I don't need a lot of time for the last of this. So our approach is always an interferometric approach.
Always interferometric.
Let's produce an attosecond pulse with one beam. I told you how you can make a very short pulse, only about a cycle or so, to create an attosecond pulse. You can be a little more sloppy by using a slightly different approach, a time-dependent electric field. Its pulse starts circular. The electron never comes back if you follow F equals ma. and it goes linear, and there it collides, and goes back circular again. And that allows you to be a little more sloppy. You can have a little longer pulse if you make it in this more complex way. And that's what we do in my lab. And then you come in and perturb that with the second beam, like an interferometer. An interferometer, you have two paths, and then one arm, you're going to perturb, you're going to have a little micrometer, and you're going to move one arm rather than the other. And this one, this perturbing beam, is really the interferometer, it's the micrometer essentially, that you use in an interferometer. These two beams interfere in the medium, creating a diffracting beam. If you think about the electron, it moves along the strong field, and so the weak field is really creating a little phase and amplitude grading on top of this really strong one. And because the electron is moving along the strong one, there is a delay as you move up and down, and so it really is a phase and an amplitude grading that's written. Now you're going to remember that
toroidal mirror
return at different fields at different times, and so a phase and an amplitude grading will have encoded in it information about when the color returned. So out it comes, a diffracted beam. It's picked up in the toroidal mirror and focused back down on the screen over here. In between, we have a physical grading, which separates the colors. And so there will be red, green, and blue. And we're going to look at the structure of that grading in here as seen by the red, green, and blue radiation. And that will contain information about the details of that.
So basically, he's saying that when we look at the different color screen we see at the bottom right here, we can tell what kind of pulses are being given off. That seems to be what it is. If I'm correct here. Certainly seems to be what we're looking at. Now, the toroidal mirror is interesting because this is what Eric Davis was saying was used potentially with the negative energy laser. He said to make a negative energy laser, you might want a long conical mirror, I think, cylindrical, which I guess you could call a toroidal mirror. It certainly looks like that we're seeing right there. So somehow there's a connection here. Somehow there's a connection here. And then he just shows some of the experiments at the end, some of the just like phase shifts that they were able to produce versus the simulations versus the experimentations. So pretty similar, pretty interesting. Okay. Let me just really quickly hit these last donos. Thank you, Mark Scott, for that other follow-up donation. I appreciate it. Tic Tac, I had to put you in timeout. You were kind of going crazy there, but laser 1 is sub-femtosecond pulse. Laser 2 is longer pulse, way higher intensity. Yeah, I think that's the whole point. Is you're trying to amplify it. You're trying to use one pulse, and then you're trying to amplify it. And that would be the point of using a laser, right? I don't know what collinear geometry, but thank you very much. Wait, so does that kill the occupants? It's a great question. Truthfully, some people have told me, yeah, it will, but I don't think so. I mean, it could. If you look at the stuff that Ken Shoulders was looking at, he says that it makes stuff disappear, but he says it's like teleportation. And even Bob Grenier, when he says it's making stuff disappear, he's saying it's going somewhere else, but it might go to like the center of the sun or the earth, which would be the equivalent of making it disappear, right? So, no, I think it's actually just zapping it somewhere else. I think that really the answer to this is going to be that what we think of as just something getting zapped out of existence might just be actual teleportation, like a bridge between 2 points in space-time. At the end of the day, what I really think is happening is that the only way this can really be possible physically is if what we perceive as our reality is a holographic projection, that we're just energy being projected from the same as like a computer, basically. The energy is being projected onto your screen. You're living out your 3D video game in Minecraft or whatever your 3D game is. That's the same as our reality. We're a projection. Our bodies are mass, but it's still just energy. And that all the points that we see and distance that we see, that's all just an illusion. It's all an illusion. being projected out onto us. That's how we can do what we can do, where we can just teleport. That's how it would make the most logical sense to me. So I think personally that's what it's going to end up being, but I don't know. I'm actually not like, I don't really have any strong biases on what I think the answer is going to be about physics and what have you. I just want to get to those answers, you know? But yeah, I'm not going to be the one that volunteers for that test. No chance, no doubt. So I think that looking at this today, what I leave being very convinced with is that this science, attosecond science, is the secret to producing coherent balls of plasma. Even though we might be able to move beyond lasers entirely, it's like if we can amplify an input laser into a more powerful output, then can't we just amplify like any small input? Can we use like sound waves to amplify into a laser? Why not? I don't know. So those are questions that I think that I look forward to exploring more in future topics. I also leave really, really convinced that there's a relationship between light and anti-gravity, or gravity, I guess is the better way to explain it, gravity manipulation. It seems very clear there must be a connection. And really, like, what is light even to begin with? It seems to me, light is just an emission of energy. When we look at it from the model there, it's like, oh, well, the electron's ripping free and then bouncing back and it's emitting light. It makes sense, but it's also like, why is the universe that way? Why is it that way? And what makes it that way? Space is empty, but how is it doing that? Is it absorbing the energy from the laser? Anyway, interesting thoughts. Fun looking at all of the stuff related to lasers. I hope you guys enjoyed it. One last thing in video I'll leave us with for our moment of Zen is, was it femtosecond laser? Yeah. I think we have this femtosecond laser plasma ball. So this was just like a backyard. This is not a laser nearly as powerful as the one we just saw. And I'm going to mute it because it's got, actually, I'm not going to mute it. So this is a femtosecond laser producing a plasma ball. I think it's just ripping the hydrogen out of the air. I think that's how it's doing that, actually. Could be wrong. I'll mute it for this last version. Anyway, guys, that's your moment of Zen. Thank you very much. Hope you enjoyed the live stream. Check it out on Wednesday, guys. Very special live stream on Wednesday, everybody. Wednesday live stream. Going to be a big showdown. Well, I don't know. Call it whatever you want to call it. We're going to talk about cold fusion on Wednesday. Two special guests, Bob Grenier, Michael Perrone, two heavyweights in the physics world, and low energy nuclear reactions expert Bob Grenier discussing cold fusion, low energy nuclear reactions. I'm gonna be honest. I'm biased. I believe that cold fusion is absolutely real. So I look forward to learning something and hopefully getting close to understanding like what form of cold fusion is going to be like the winner. So check us out on Wednesday for a special Hard Truths podcast. Cold fusion, Michael Perrone, and Bob Grenier, guys. See you guys Wednesday. Oh, also 6 p.m. Wednesday Central Time, 1 hour early. Be there. Peace, everybody. Love you guys. MH370X out.
In the fields where the skies are wide, talking about a journey through the cosmic ride. Einstein and Thorne, they set the stage for a trip through time across the space age. Wormholes connect distant points in space, traversable paths to a far off place. No black holes pull, no crushing weight, just a cosmic tunnel to a distant gate. Talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Bowling 777 through a wormhole flow. We're talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Bowling 777 through a wormhole flow. exotic matter. Negative energy's the key to stabilize the wormhole for you and me. Quantum vacuum squeeze so tight, creating conditions for this wondrous flight. Static fields and lasers in the lab they play, generating forces in a new kind of way. Gravitational squeezing, Casimir's force, negative zones we need to stay the course.
Talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Boeing 777 through a wormhole flow.
Thin shell formalism placed so fine, spherical geometry we realign. Energy conditions that we must defy. For a stable wormhole, let's give it a try. Unknown forces balancing the plates, creating the throat, open the gates, from Earth to the stars in a single bound. A shortcut through space profound. Engineers and dreamers hold the key to future worlds and what we could be. With science in hand, we forge ahead through the cosmic paths that we now tread.
We're talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Boeing 777 through a wormhole flow.
From the fields to the stars, we break the chains. Understanding the universe, we make the gains. Lil Hula Crunk shines, bringing truth to light. Through his music, we'll explore the night with wormholes.